So the common ratio, R, is just found by dividing two successive terms with each other, okay? So now, let's take a look at this one and find the common ratio here. We're gonna take R, A2 over A1. Again, order will matter, right? You can't do A1 over A2. So A2 over A1 is gonna be negative 9 over 6, which is negative 1.5, right? And if we wanted to find the next three terms, we're just going to take each of the terms and multiply by negative 1.5. So I get 20.25, and then do that again.
Negative 30.375.
Right? 45.563. I will have specified all that, okay? So those are the next three terms. All right, so for one like this, R is the same thing basically. So it's negative 81n plus 243 over 243n minus 729. So it's, when I factor out a negative 81 here, I get n minus 3. And when I factor out a 243, I get n minus 3. So my R is negative 1 over 3. So the next term is going to be negative 1 over 3 times 27n minus 81. That's negative 9n plus 27. Then we're going to multiply that by negative a third. And we're going to get 3n minus 9. Then I'm going to multiply that by negative 1 over 3 and get n minus 3, negative n plus 3. Okay? Right. Okay, so let's think about some patterns here. All right, let's think about some patterns. Suppose you have a geometric sequence for which R is equal to 2. All right, and suppose A1 is equal to 3. Then what would A2 be? 3 times what? 2. And what would A3 be? 3 times 2 times 2, right? And A4, 3 times 2 times 2 times 2, right? In more concise form, this is 3. This is 3 times 2 to the 1. You see how like you have a series of 2's here. And this is 3 times 2 squared. And this is 3 times 2 cubed. Well, what, why? Okay, so we don't want the first one to be left out. It's 3 times 2 to the what? 2 to the 0. Right. So, okay, so then if we go down the line to AN, right? What is that going to look like? So what do all these look like? What do they all start with? What's the 3 though? What's the 3 really? That's A1. What's 2 though? R. 2 is R to the power of n minus 1. And there's the formula. Just sitting there. Okay? Just sitting there waiting. So this formula it just logically is what follows, right? Because how many did we do? 1, 2, 3, 4, right? And we already got that it's A1 R to the n minus 1, right? It's just the result of a pattern, yeah.
Is it possible to have a sequence, geometric sequence where like each number, like the ratio goes up by 1 or something like that? Or is that not?
So, like if the ratios are not the same?
If the ratio increases by a certain increment.
Yeah,
You know how we did the second difference thing?
Yeah. Let me think about that. Because that was, okay, let me think about that. So let's think about what this looks like. Okay? Let's think about what this looks like. So basically, the arithmetic series, right? AN was equal to A1 plus what? N minus 1 times D. So what was that? We said yesterday that we could have written that as y equals mx plus b, right? Right? It was a linear relationship, yes? So that was linear. Well, let's take a look at the geometric then. AN is equal to A1 r to the n minus 1, okay? If we write it as not A1 but A0, right, it would be AN is equal to A0 r to the n, right, because it would be one less, okay. So, now what? Okay, so AN, is that changing? It's changing, we call that Y. A naught, is that changing? No, let's just call that A. R, is that changing? Let's just call that B. N, is that changing? It's changing. What does that look like? It's an exponential function. Right? It's an exponential because each time it's 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. It's an exponential function. Okay? More on that later. Okay. Yeah, stay tuned, like in 5 minutes. Okay, so explicit formula, recursive formula. We know how to do this now. So here we go. We're going to figure out what R is. In this case, R is negative 2 over 1, which is negative 2. A1 is negative 1. So the formula, the explicit formula, the general form, is AN equals A1 R n minus 1. Yes? So AN then would be negative 1 times negative 2 to the power of n minus 1. And whether you write that like that or like just with a minus in front, it's up to you. But basically, this is the explicit formula. So with this, if you want to jump down the line and find A sub 81, you could just do it like that. Okay, now what if you have A sub 81 and then you want to find A sub 82? Let's see what recursive formula we could come up with. So for the recursive, we're going to give the value of A1. And AN, how do you get AN in a geometric sequence? So, or how do you get, okay, so if you're going to get one term recursively, what do you do to the previous term? Multiply by what? The ratio R, right? So it's going to be AN minus 1 times R, okay? So in this problem, A1 is negative 1. So AN is going to be AN minus 1 times negative 2. But that doesn't look nice, so let's make it look nice. AN is equal to negative 2AN minus 1. Okay, so that's telling you how to get the next one based on the previous one.
Why is it negative 2?
That was the R. Okay, so 11th term, so far pretty boring. We need to find A11. This is A1. Well, what's R? R is 115.9 over negative 122. Yes, they're not all going to be cute little integers, and that's just fine. R, it turns out, is 0.95. Okay? So AN, we know is A1, R to the n minus 1. A11 is negative 122 times R to the power of 11 minus 1. And I know you all know how to put that in your calculator. In fact, I did that, and I got negative 73.05. Okay? Does it make sense that it's a negative number? Well, it's alternating between negative, positive, negative, positive. It looks like the odd terms are negative. So yeah, it makes sense. The values are going down by 0.95, close to a 1, you know. So, all right, it's not going to go down too much, right? We got to reason these out, okay? It does, because you're going down 11 times by like close to 0.1. You're multiplying by 0.95. That's very close to a 1. That means the next one over is going to be close to the previous one. So close to the previous one, close to the previous one, and it makes sense. Okay, geometric means. We talked about arithmetic means. Geometric means are the same thing. They're basically the terms between two non-consecutive terms in a geometric sequence. Okay? So here we go. We know how to do this already. We need to insert 3 geometric means between 264 and that number, 1.0, blah, blah, blah. So 264, we're going to put in 3 new ones, 1.03125. What's my n? How many total numbers? 5. And I know what A1 is. It's 264. Okay, I just don't know what R is, but I can totally find R, right? Because A1, AN is A1, R to the n minus 1. So 1.03125 is the first number multiplied by R to the power of how many? 4, right? 5 minus 1. Okay, so divide. Word to the wise, don't round in the intermediate steps here, okay? So we're going to divide by 264, and that's going to be equal to R to the 4. How do I get rid of the 4? To the power of 1/4 to the power of 1/4. Guess what R is? Oh my God, it's 0.25. Okay, it's a quarter. All right? This 4 was n minus 1, n was 5, minus 1 is 4. So 264 divided by a quarter, 66. 1/4 of that is 16.5. 1/4 of that is 4.125. And guess what? 1/4 of that, what is that? Yeah. Okay, so geometric series. Let's think about geometric series for a minute. What did we say a geometric series looks like? Was it linear? It was exponential. Okay, so we said a geometric sequence is exponential, right? Okay, meaning if I have AN is equal to A1 times R to the power of, let's just say A0, R to the n. What does an exponential graph look like? Okay, some of you guys are telling me that it looks like this. Or if it's decay, it looks like that. Yes? Huh? Right, okay. What would the, okay, so what's the difference in the function for one graph versus the other, for the left? Exponent is negative, meaning what? Meaning what about R? What about that?
R.
Not positive or negative.
Oh, 1 between
Greater
0.
or less than 1?
Yeah. Oh my God.
Greater, okay. So if R is between 0 and 1, it looks like that. If R is greater than 1, it looks like that. Okay? So the reason why I bring this up is talking about geometric series, they get very big very fast. So when you're going to add a series, right, the sum of the series, look at, it could get very, very big. Or if it's approaching 0, it could be a very finite number. The sum of it could be a very finite number.
If it's less than 1 or less than 0.
Well, okay, it's the absolute value. Okay, it's the absolute value of it. Okay, so let's talk about, let's try to derive a formula for the sum of a series. Let's see what the sum of what Sn looks like. Okay, I have A1, that's my first term. And then, does it make sense that the second one is A1 times R? Yeah? Does it make sense that the next term then is A1 times R squared? Because I just add another R. So, going down the line, I'm going to leave a little space here. The very last term, An, we said was, leave some space here. We said it was A1 R to the n minus 1, right? Yes, we did. Okay, what's the term right before that?
N minus 2.
Oh, okay.
Oh, another one of these.
Oh, it's all going to cancel out.
Oh,
no.
I can't do this right now.
Now look at what we're going to do. Luckily, okay, now look at what we're going to do. We're going to put another Sn here. We actually are. Have you seen this before? Have you seen this episode before?
Alex.
Oh.
I'm kidding.
Okay, so we're now going to start from the back. Okay? So I'm going to start with, or no, you know what? No, you know what I'm going to do? I'm not going to add Sn. I'm going to be a rebel. And I'm going to add R times Sn. Oh my, oh my. R times Sn. So now, the first term then gives me what if I multiply it by R? A1R. So I'm just going to write it here to align them. Then if I multiply the second term by R, it'll be A1R squared, plus, then I'm going to have an A1R to the minus 2. Okay. R to the n minus 1. Okay, so let's start multiplying from the back. Let's start multiplying with the back. If I multiply this one, by R, what do I get? It's A1, R to the n minus 1 plus 1, A1, R to the n. So that last term, if I multiply it by R, it'll give me A1, R to the n. If I multiply this, it'll be AR n minus 1, and then AR n minus 2. So I'm going to have one more term here, R to the n.
What's that for?
This one?
Yeah.
R to the n minus 2, R to the n minus 1, R to the n. Now, you know what I'm going to do? Subtract these. And of course, I'm going to go by, no, I'm going to, I'm going to subtract them. So here, I'm going to get Sn minus Rsn, and that equals A1 plus what? No, I'm subtracting them. That's 0. I'm subtracting them. 0, 0, 0. Here, 0 minus this, it's minus, oh, is that what you were saying? Minus A1 R to the n. Okay, let's factor out an Sn, and that'll give me 1 minus R equals, and let's factor out an A1 as well, 1 minus R to the n. So Sn will equal A1, 1 minus R to the n, over 1 minus r.
And I think the formula might be waiting for us in the next page.
Is it?
Of course it is. Oh my goodness.
Oh my goodness. Okay, so you see where these came from. The reason why I do this is because I want you to see that these formulas didn't just drop out of thin air on somebody's paper. Somebody, okay, somebody like you sat down and created these. Like, not created them, but they came, like they derived them.
During their all school shopping time.
That's pretty much where it happened, yes. So, shh. So, I'm gonna take this step and I'm gonna solve it for Sn. So I'm gonna distribute the A1 as well. So A1 minus A1 r to the n over 1 minus r. Okay? Okay. So this is gonna be A1 minus, okay. What is this, guys? Can I write that as
Oh, negative A1.
A1 r to the n minus 1 times r? Can I write that? Because look, it's exactly what I did here. Okay? Right, I'm just going backwards now. Okay? All over 1 minus r. Okay? But this is A1 minus. What is this? What is this from before? Where have we seen this before? It's AN times R over 1 minus R. Shh. That's the first and second formulas here. First, second. What happened there? Oh, it's 1 minus R. Okay? Shh. Okay. Let's do this then. The sum of the first 11 terms of the geometric series, this one. So first we find R, and then S11 is what we need, and that's just going to be formula 1. So A1, which is 4, 1 minus negative 1.5 to the 11 over 1 minus negative 1.5. So S11 is 140. I mean, no, it's 4 times.
No, like, when it says all the cars, I'm going to
11. N is 11. We're finding the first 11 terms. Okay. I need to do these next two as well. Here. Oh, and I have this other page. Okay, let's pick up the pace here. The sum of the first n terms of the geometric series. So A1 is negative 4. We're going to use formula number 2 here. Okay? So we're going to plug them in. It's going to be negative 4 plus 2 times AN over 1 minus 2. So Sn is negative 131,068. Right, but it's negative, negative, positive. Okay, when you have sigma, okay, this number that's being raised to the exponent, that's your r. Okay? So now, I need the sum from n equals 3 to n equals 8. That's a total of 8 minus 3 plus 1, 6 numbers. The first term is when n equals 3, and that's negative 8. Okay? And that's really all I need, because Sn is A1, 1 minus r to the n over 1 minus r, That's negative 8. 1 minus negative 2 to the 6 over 1 plus 2, 168. Okay, now, the derivation for what if it's an infinite series? Infinite series, all I want you to, I'm not going to derive it, but all I want you to think about is this. Like we said before, when r is greater than 1, the numbers are going to get infinitely larger. And if I'm adding up all those numbers of an infinite series that never end, I can't, because the answer is going to be infinity. So it only works, you can only find the sum of an infinite series, geometric series, if r is less than, between 0 and 1. Okay? So this is the formula for an infinite series. It's much simpler actually because you don't have an and all that good stuff. And you only use it if r is less than 1. Right, it works for 1, doesn't work for 2. And I'm not going to do either 1 or 2. I'm going to do number 3 because this is r, right? And since r is less than 1, it works. And this is an infinite series, you can see here. What's the first term? 3 times 0.65 to the power of 1. It's actually 1.95. So S is 1.95, 1 minus 0.65. So look, you take a sum of an infinite number of numbers, and it just turns to 39 over 7. How cute is that? Okay? So this homework is due
How can there be so many infinite
the day you come back.